All right, other one. I had a great week.
That's so good.
I fixed those telescopes that were all messed up, collimated them, so we can take even better observations. I was really worried that it was going to be actually something bad. And I did what we call work on the weekend. It's very annoying, but it was very responsible. So, okay. What were we talking about? Does anyone remember?
There was how to find the attraction between north, south, and hemispheres.
Right, using tensors. Specifically, which tensor?
T.da.
T.da. What did that mean? Yes, very close. Force, right? So that was specifically coming from something called the Maxwell stress tensor, right? That was the T that we talked about. T for stress tensor, right? Maxwell stress tensor. Okay, and specifically what we wanted to do is we wanted to find out whether or not we could generally think about forces between two objects, right? So we had these two electrons, remember? We found that their forces were not equal and opposite. And I made this really crazy statement that somehow the fields themselves carry momentum. And no one stopped me because they were like, whatever, there's money, you want to break the laws of physics, that sounds fun for a Tuesday. And then I went on this whole rant about stress tensors, and you had to remember fluids, you know, like, this is stupid. I deleted that class for a reason. And then you were like, wait, it kind of seems powerful because, no. Okay, well, to some people, you might feel like it's powerful because all you have to do, and I say all kind of hand wavy, what you really have to do is to calculate the electric field, and then you calculate the magnetic field, and then you simply integrate them over a closed surface, and that gives you the forces between them. And they can be completely arbitrary, right? So I grabbed some inane problem of a sphere with charge on it, and then I spun it, and I said, go for it. And it's actually straightforward. Now, we could do all the math, but I don't think we'll want to. Is that correct? Do we want to finish that math? Raise your hand if you want to finish the math, because we're going to see an example of that again. So later on, we'll look at an example of, say, a coaxial cable. I'll give you the starting to one of the homework problems, right? And we'll see this Maxwell stress tensor more. And then we'll head into what I think is the fundamentally most interesting part of this class, and something that we'll use for the rest of our lives. So just to finish that question, you know, maybe I can set up this Maxwell stress tensor and we can remind ourselves, but let me show you what the math looks like. Okay. All right. So this is how many pages finish that problem. Well, look at that. That's a pretty answer. You see it at the bottom here? It's just this one line. So I can set that back up again, but I think it may be more instructive to do a completely different problem in the same way. Okay, and that'll get our brain working, because this one is only 2 pages. And I was looking at the options here and I was like, okay. So to continue to motivate you as to why we care about where we're headed when we're thinking about the next week, and you know, I think we'll finish up chapter 8 today, or the things that I'm interested in chapter 8. And we're going to jump into chapter 9. And for the first time, we're going to be able to answer, hopefully, a question that has bugged you for your whole life, right? And that is, how does light propagate in space? Right? That's the first thing that you got out of the womb and you were like, damn, how light be out in space? And in fact, this is one of the most important questions, right? Because if not for light, we would have no information about any of the other stars. We would not understand how the universe was formed. We would have no conception of anything you know, outside of what we could touch and smell and hear. You can't hear in space. Unlike what Star Wars shows. Okay. Okay. So hopefully by the end of next week, you'll have a beginning of this understanding of how a time varying electric field and magnetic field work together to propagate in a vacuum. Oh shit, life's so cool. And you'll forget all about atoms and electrons. Okay. So we were talking about the Maxwell stress tensor. And just for clarification again, what does that look like?
Oh, is it like in the first row, it's like TXX, TXY, TXG?
And generally speaking, I would do it like this. Tij. Let's say I want to write each component.
Oh, like this.
Summation.
Right, yeah. So if I wanted the whole tensor, I would sum it, but if I just want the component, then I'm gonna write it. This is called component notation.
Hmm.
So if you see two of the same, so if I did TII, that would mean that I would want to sum over a single index. But if I write Tij, this just means I'm giving you the formula for you to make it up at home. Right? So how would I write this? We know there's an epsilon naught because there's an electronic side. And we know that there is a plus 1 over mu naught. There's a magnetic side. And there's a beautiful symmetry, and that is
in the first like parentheses like EI times EJ minus 1/2 I'm gonna call it
Or correct delta.
yeah.
close, all right. Kronecker delta. Let me write it down, and I'm gonna write it wrong because I obviously don't know how to spell. This is the direct delta function is exactly the same symbol. Identical symbol, but it has an argument. And that argument means that when that argument is 0, then you get 1, and when it's not 0, you get 0. Whereas the Kronecker delta uses the same delta, but it has these two little indices. Right? And the fact that it has these two indices is just saying when the indices match, you get 1. And when they don't match, you get 0. So they behave the same way. That's why they get the same symbol, but they do something slightly different. And what goes here? All right, now without looking at your book, what goes on the other side? Same thing with B. Right, that's the beautiful symmetry I was hinting at. All right, very good handwriting. Okay. I want to fully understand how to use this, right? So the trick here, we're looking at this thing. We're going to calculate the stress tensor. First, we have to evaluate the fields, figure them all out, and then we just look at the components. So this is Bx, or right, Bx times Bx, or Bx times By. If this was Bx times By, this is Bx times By, then this would be 0. Good. And if this is Bx times Bx, then it's Bx squared, and this is
1.
1.
1/2
You will, okay. 1 times a half, good. And then this.
is the
B
B.
squared over 2.
Now this is really important to remember, right? Like she just said, it's B squared, not Bx squared. Right? So this is not component wise. This is the total field. Okay. That's just a small detail, and we'll see that when we do it right now. Okay. So generally speaking, we use this to get this very powerful force equation. And that was. Alright, so what the fuck did I write?
That's like the individual was.
Yeah.
Like the right side, like how much fuel is going in or out of the system.
Yeah, something like that, right? So this was like the pointing vector. And we thought about it in the context of like transferring something. In this particular context, this is the transfer of momentum with time. Okay, and that's what we call a force. So this is a force term that comes from the fields changing. Whereas this one here is the Maxwell stress term. And these can be electronic or magnetic pressures or electronic or magnetic shears that create force. Does that make sense? Okay, yeah. Yeah. So just like we thought about when we thought about a fluid, you can have a fluid that compresses, that's a pressure, or a shear. These ones here, the Maxwell stress tensor permits for there to be magnetic and electric pressures and magnetic and electric shears. So what do I mean by that? If I take an electronic, say I have a wave, and I press it, I move that electronic wave towards a bunch of electrons, what do?
Wait, sorry.
Take a wall, let's say I can build a thick wall of electric field. And here's a whole bunch of negative electric field, and then I move it towards you and you're all electrons.
Okay.
You go away.
Yeah.
Right? So the idea of pressure, so I'm moving an E field in the direction, right? It's not exactly the right idea, but it'll get us there intellectually. Okay, that's what we call an analogy. Okay, don't believe what I'm saying. Make sense? Okay. So that's the way this term acts. Right? And what I'm looking at then is two different force terms. Okay. All right. So now here's your problem for the day, or one of many. All right. You have a charge. You have a charge Q plus. And a charge Q plus. And you have some distance R. Okay. Have some angle alpha. Another angle here. Some height S. The distance A. It's okay. Okay. So now the question is, what is the force at this location? And you're thinking to yourself, oh, just use F equals QE. No. Let's do it the hard way. I know it sucks, but it's worth it. Oh, sorry, I should be more clear. What is the force of them on one another? Not this random point.
Okay, so I was gonna ask, like, are they moving towards them?
Now, this would be extremely simple if you just use QE. We were on purpose going to do it harder to show that you get the same answer. To practice using it.
Okay.
Right? That make sense? What?
How would you use QE?
Well, what's E?
Electric field.
Yeah, what's the electric field of a point charge?
Ow.
That's fine.
Just Coulomb law, right?
Fine.
There's just one over R squared.
Oh, okay.
Wonderful. Trying to do all. To know that she must be the probably fine. And then I forgot to make it.
The Q squared?
Well, if it's point card, then you're trying.
Oh, yeah.
It's not-
I think it-
Then we have to keep. Yeah.
Yeah.
X. Then it's C, it's a one. Yeah.
So the, so this is time to be now. Those kind of going off on home business.
Okay.
At each other.
Yes.
Dude, I asked for friend if you're. Stop it.
I'm gonna go in. this time.
Oh.
So what I did. So the R hat, I was making R vector. So what is R hat? R hat would be like X hat is Y hat.
Yeah.
So then I just like. Did like.
Cool.
Yeah, so I like R hat. You do that, so it. So it's like.
So this would be
So
field.
I got my R hat, thinking about mine.
No big deal.
X hat.
So it's not moving?
Y hat.
No, but that's right. No, that aren't.
The very least we have that,
No, they're not moving.
That's not.
They're not moving.
They're not moving, no. I'm drawing this to demonstrate how to write some coordinate systems. Now, if we think very carefully about this problem, we'll see clever solution. Oh,
I think that's the they're moving.
There we go.
oh, no, sorry. This is just, the distance to a point on a plane between them. You might be thinking to yourself, why would I need a point on the plane between them?
I said they.
Remember that we're not just calculating t, we'll need to integrate t
Over here.
over an area. So where's a nice area? Yeah, what about the midplane that I just drew?
no, but I think you're looking like when it's like. Electric fields go out regularly, and then I just. No, like, I mean, like, that's a new revelation. So,
What's wrong?
I wrote down
I
that
don't know
R
if I
hat
need
is
to.
X and Y to equal one.
Okay.
Okay.
Why?
Okay, let's break this down.
I'm spitting.
Let's break down what we're doing here, okay? And we're gonna think at a very high level. We're gonna forget everything we've ever known about QE. I know. We'll remember it in a few minutes. In like 25 minutes, okay. But right now, let's just think carefully about how we would approach this problem. So what we're saying here is that we're trying to calculate the force between the two. Yeah. And so we want to know what we can ignore. So let's start with this term.
Yes.
Oh, is this varying?
So E cross B makes the S, I recall that, so let me write that down so that everyone has this in their mind. This is the pointing vector. And of course, this is E cross B. So what do we think S is? 0. And why is that?
There's no moving.
Exactly. B is 0 because there's no moving charge. So good. So even before we get to here, from the fact that it's not moving, we doubly know that this whole term is 0. So half of our problem is already done. So let's look inside of T dot dA. Now this integral over an area, I just need to like select a surface and I'll be fine. Okay. So let's use a symmetric surface because I like symmetric integrals. And I'm just going to choose the midplane between them. So I've chosen my place. And now I need to think about what the hell T is. What the hell is T?
From that top equation right there.
The
Right.
T part is 0.
Good. So for the same reason. Right? Reasonable? Cool. So we're in really good shape. So now we have to make some fun choices. Okay. So if I say that E, let's say this is Q1 and Q2. E1 in spherical coordinates is what?
Oh, it's variable.
Uh-huh.
Yeah, so they are.
Fight.
It's a Q over 4 pi epsilon naught r squared.
Okay. That reasonable? You're missing something?
R hat.
Very good. That's it. I didn't write the vector symbol to you. Okay. So that's spherical coordinates. However, if we want to add E1 to E2, is spherical coordinates the best choice? No, not really. Because you lose the fact that it's spherically symmetric. But a fun coordinate system is cylindrical. We can write I'm going to write it by components. Let's start with E. Right. Because of symmetry, right? So these cancel, and this was also shown in a problem back in chapter 2. I know you haven't memorized all the problems, but
T's going like up. Right?
what's that now?
T's going up and then R is going.
So this is R, so this is the R direction. And then this is the phi direction. R,
So C
phi,
is-
Z is this. Okay. E phi. What was that? 0. That's also 0 by symmetry. Right, because I told you this would be nice. I didn't want to make it harder by switching into a new coordinate system. So along this line, E5 is 0, right?
But can you explain that? And which way is 5?
So if I'm here, I'm not getting pulled up or down. I'm only getting pulled out.
Oh,
What's ES? This is the hard one. That's pretty good. I do have to add in one more thing though, because this is now going to be misaligned with the distance here. So I'm gonna write something along the lines of let's write that R hat, when we write it in the S direction, is defined as cosine alpha, using that alpha there, in S hat direction. Okay. So another way of writing this is that I'm gonna write it like that. I'm gonna write S over R. And we're okay with that. That's what cosine means. Right.
Yeah.
Everyone likes okay. No, sorry. Okay. So I can write the ES is going to be E1S plus E2S. Okay. And I know that E1S is the same as E2S in magnitude, which is the same as 1 over 4 pi epsilon naught, as we wrote before. I'm going to borrow some of that language here, but I'm just going to write it like this, Q over R squared, and then I'm going to change from R hat to S hat. So it's S over R hat. That's right. Those are all the same pieces. All right. So now I need to add them. That's what this says to do, right? Okay, so I got R cubed on the bottom, I got S on the top. Okay. And this is at a specific location, A. Okay. I'm writing S evaluated all up and down this line. This is going to be something like if you're thinking to yourself, Mateo, you're not really showing us. That's because this will be a long problem. Yeah. So ES squared is
That's a lot of things.
just that thing, right? So we could do Q S for 2 pi epsilon naught 1 squared 1 over S squared Q. Right? Okay. And then you'll figure it out. You'll get some really nice answer. And you'll get to the very end and it'll be exactly what you thought it was from QE. So you'll be able to check your work really easily. But the real trick here, right, is simply looking at the components. So once we've written out our ES properly, our E5 properly, our EZ properly, right? We can look here and we can say in this coordinate system, which matters? So EI, EJ. What's that? Only the one that matters is S, and everything else will disappear. There's only one term to consider. It's awesome. Which is not even the diagonal term. There's one of the diagonal terms. Because all the other ones are garbage. So you have this huge tensor with 9 components in it. All the off diagonals are 0 because it's 0 times something. Then 0 times itself is still 0, so the bottom two diagonals are gone. And the only diagonal that matters is the ES squared. And I just wrote it and it seemed relatively fine, right? Okay. Cool. Questions about how to use this?
Like, how do you get the cosine alpha from R? It had to just get that.
That's the. So this is the. So
Yeah,
so here's the angle. Right? Sorry, I don't know if that's helpful.
I know how cosine works. I'm saying, how would you know the relationship between R and S is cosine?
Because this is the angle here.
We're given as.
Like.
Or given as.
I just wrote, no, so hold on. So I know where I'm going and you don't. And where I'm gonna go is I'm gonna need to integrate along this entire line. So I'll need to integrate S from 0 or -infinity to infinity. Right, so I know that I'm gonna need to do that integral. So I just wrote it in those terms. Is that helpful or not?
No.
Okay. I used some double magic. I used double magic in order to start with a coordinate system that made it really simple. Because it's already going to be stupidly hard to do this part, right? We're learning all these different things. And if we just accept, we just wash our hands clear of a weird choice, right? Because I know in the future that I'm going to have to do this integral along this line. So remember that this is really a surface between these two objects. Similarly, when we have these two spheres and they're rotating, and I want the force on one half from the other, what I have to do is bisect them, cut them in half, and then integrate the F through the T through that surface. Make sense?
Yeah.
Okay. So similarly, I'm looking for T dot dA, the component that's going through dA. Right? And I'm saying to myself, oh, okay, that makes sense.
Good.
Yeah. It's a little, yeah.
In other words, it shows that because we know that there's no tensors in
In the angle direction.
Yeah, well, we know we're gonna have to dot it into dA, right? So that's the surface in this direction. So I only want the stuff that's in that direction. Okay. This will hopefully make a lot more sense when you do this problem. I'm gonna remove some of this now, is that okay? Let's talk about the reason why we motivated this tensor at all. And that was momentum. What?
The eraser's terrible.
Whiteboard. And sometimes it's nice, sometimes it's awful. Like this one's fine. Ish. I don't know. That's good, yeah. All right. Let's talk really quickly about momentum. Now, I brought these other colored chalks. Which one is which?
All the.
Lewis power.
What?
Lewis power and complete momentum.
Blue is power, pink was momentum, right? Good, all right. I'll hold on to this. So we wrote the electromagnetic force as a tensor, right? Or sorry, I should say it differently. We wrote the stress tensor, and we can get the force from that. Okay, and we wrote it only in terms of the fields, the things that are communicating these forces. Okay. So what was Newton's third law again? Or sorry, Newton's second law? You'll all be shouting.
Yeah.
I cannot give you a degree if you can't shout that at me.
Yeah.
Okay, F equals. MA, good. Alright, and that's what we teach in 2500.
Mhm.
But then you take classical mechanics and you actually learn
M is equal to AD over D.
M is equal to that?
Oh, sorry, F is equal to M times AD over D.
Like that?
Yeah.
Okay. Okay. Almost. Maybe that's your first semester of mechanics. So you get to graduate mechanics and you learn dPdt. Very good. Okay. And that's why I have to write two.
Oh, no. Yeah.
Won't be moving at all.
It's-
It's, but it's blue for power. I don't know. Alright, this is P for pink and momentum. Maybe I should have switched them. Alright, it's too fucking.
I think it's confusing no matter what.
Yeah, it's not gonna be good. Okay. Alright, so this is really the way that we talk about Newton's third law. Because as we know with rockets, we can change our mass. And that will give us a force. Right? We can increase their velocity, that will give us a force. Okay. So if I can think about this piece here, okay, as the rate of change of the momentum, then I can get a force. Let me write this again. In electromagnetism, what I just wrote on the board is minus mu naught epsilon naught. I'm reversing the order here, but that's fine, you won't cry about it. Then. So where is the momentum stored in the field? Yes. I said yes to both of them, they said two different things. But I heard the pointing vector first.
Yeah.
So why is it the pointing vector? If you're teaching it or not.
That's what you need time.
That's the one changing time. So if we look at this piece here, DDT, this must be the momentum from the fields. Okay. And then what's this?
Oh.
Okay, okay. This one's less intuitive. So we said that that one was the pressure, sorry, I saw P, I said pressure. We said that that was the momentum from the fields. And this one here, because we're looking at a surface integral, this is telling you how much of that momentum is leaking through the box. So if I'm a momentum carrier in this problem, and I go through the door, I'm in the second term. So this is momentum. In or out. Okay. Okay, so I can write this one. So P in electromagnetism in the fields themselves is written. Okay. And you might be thinking to yourself, I saw that before. You're not thinking that? Yeah, you're thinking that, right?
Yeah, I did last time.
Yeah, but what do we do specifically in another class? What is the power? What's that?
I actually said this one blue.
God, I hope not.
No, we were speaking specifically about power,
Yeah, we were.
right? And we'll go back and we look in our textbook and go, Prismani, that looks so similar. What the hell are you talking about?
It's like the. It's like S dot DA with like the power.
The power communicated was
The closed interval S dot DA.
and what was power again?
One more time.
The change in energy time. So this is telling us something really interesting that I just want to like point and reflect to right now. Okay? So this is telling us that the pointing vector is talking about energies and momentum being transferred. Okay? So not only do we have the ability to think about them in the context of, okay, they can hold on to this energy and they can transport it. They can hold on to momentum and they can transport it. And the major differences is this is the volume integral of the pointing vector. This is the surface flux of the pointing vector. Okay. So this is the momentum stored in the fields. And then this is the energy transferred by the fields. Okay. Okay. I can say this a bunch of different times, right? You're not gonna get upset. So we'll just hammer this point home. Okay. So specifically, we're gonna say that dt what this essentially says, another way of re-looking at this piece here. The momentum change in the system is due to the momentum brought in or out of a surface by the field. So this is the momentum being brought through the surface, the closed surface dot dA. Okay, so I said that before when I talked about myself being momentum and going in and out of the door. And now I've written it in a more smarter looking way. So this is the rate of change, F, dt dt, and now I've broken it up. Okay, I have an electromagnetic momentum and the mechanical momentum. So to increase or decrease the momentum of the system, I have to bring it in from somewhere. Okay. If you wanted to, you could use Gauss's law. You could write that with. Okay. Cool.
That's that arrow thing, we did say tensor.
If it's got the two sides to it, it's a tensor. It's got one, it's a vector. All right, does this remind you of anything?
Oh, it reminds us the total energy of electric and magnetic fields. Like total energy stored.
Okay, yeah, that's one way to think about it, right? We think about the total energy as a function of time, and that's equal to something else. Does it remind you of anything from fluids? Stop it with the fluids, Chris Mine. Continuity equation, right? So this here is a conservation of momentum equation, which is what we're going for. Okay, this says the rate of change of the momentum is due only to momentum leaving or entering the system. I cannot generate momentum out of nothing. I need to bring it in from somewhere or have it leave. Does that make sense? Okay. And you may have seen something similar when we talked about charge conservation. Right? That's that.
The changing charge density is equal to the.
There you go. Yeah. And we can say it, we can take these really complicated, annoying algebra, and we can boil it down to the most communicable math, right? So I got a little nephew, he's 3 years old, and I say, you know, you want more charge in this room? You gotta bring the chargers in. That's all that says. Right? Tell him, preach, no. Okay, no, but that's literally all this says. You want more chargers in the room? Bring them in. You want less chargers in the room? Take them out. Right? Okay. So generally speaking, we can define this thing here, the Maxwell stress tensor. You might also think of that if you look at this formula here. So the rate of change of the momentum is equal to the divergence of the Maxwell stress tensor. What is the Maxwell stress tensor? Let's look at that parallel for a second and see if we can understand it better.
Also, just it's telling us like the momentum in certain directions.
Okay. So what does J mean?
Oh, look at that. That's volume density, the volume current density.
Right. Right. So volume current density. And that is a way for me to understand how all of the charges are moving within a volume. So they have some organized pattern or not. That's given to me by J. So the rate of change of the charge density is due to the divergence of the charge current. Okay, so using that analogy, the rate of change of the momentum is due to the divergence of what? Almost there. Farther than that.
How much momentum is moving by the
Right. So if I use the analogy, or analogy, that would be the momentum current. Well, that's dumb, don't say that. Okay, so but the analogy is there, right? This is the charge current. So this is the momentum current, but we don't really call it that, we call it flux density. Because that sounds way cooler. And anytime you can write flux down on a piece of paper, you really feel like a scientist. You know, Back to the Future style. Okay. So in fact, we say that minus T is the momentum flux. Right? It'll take one line. How do we write the angular momentum stored in a variable? Is there any? First question, is there angular momentum stored in a field?
No.
Wow.
Yes.
Good guess, 50-50 answer.
Then could be, you know,
Okay, alright. So we can't generally say whether or not they do. So if they did, how would we find it? Right from the angular momentum, anything.
well, it's a D rate, like angle.
Okay. How do you find the angular momentum of a ball spinning?
Using torque?
Okay. Okay,
With I.
yeah.
No, I.
Oh, I'm hearing torque, but torque would take us in the opposite direction. Right, torque is with our angular acceleration.
Yeah.
Angular velocity, we might need something like that. Yeah, I'm giving you a pass because it's a Tuesday and I know that it's early. So L, the electromagnetic angular momentum is simply R cross E.
Oh, yeah.
Which.
Oh yeah. Good morning, which P? I don't know which P. Yeah, the angular momentum is in fact the P for a moment. Very good. Okay. So this one we get for free. Because we just found out what P was. Okay. Okay. So I promised you another example. I know you love examples and you feel like you're really learning and you're learning an example on your own, right? Okay, so let's do our dearest, oldest friend, the coaxial cable. No. Okay, let's ask the following question. Okay. Here's our coaxial cable. What's the momentum? You can point it.
There's no magnet. Oh, there is.
Yeah.
Nice try. Yes, last one.
How can I simplify this?
People call it like the outside or
The need to. Eyes going in one direction on one and eyes going the opposite direction on the other.
oh we use those.
Yeah, don't have it.
I have.
Yeah.
Ask the audience.
Oh, yeah. Yeah, that's right, yeah.
Yeah, okay.
Oh, interesting. Did we do it before?
Yeah.
Yeah. Didn't we do this at the very beginning? Almost 2 weeks ago?
I lost it.
Okay, so how do we do it? How do we possibly solve this impossible problem?
Always find.
Well, we can probably play.
So EB, right, that's first. And you looked over here correctly, you pointed out that you probably need something S. But you know in your mind's heart now that S is really E cross B. So I do need EB. And then you said to yourself the very important Rolando question. B? Can I get out of this? Right? Oh shit, there is B. Oh, that was your question? Okay, B, I just heard from this side. So there is B. So unfortunately we can't wiggle our way out. There's no E? Oh, there is E. All right, so we can't wiggle our way out of that either. And then we said to ourselves, okay, this wasn't so bad. Because outside of both of the coaxial cable from here and here, once we're outside, E is 0. Okay, and when we're inside of I, 0. So we really only have to calculate this interior region. And we were like, that's fine. I'm okay with that part of my life, right? Because I know what one of them is. So all I have to do is calculate the B field for I. That's pretty simple. That's something like this, right? And then the E field was like that. And it turns out that that direction and that direction, they can be crossed. Right?
With the E field is radially outward.
Yeah, why is the E field radially outward?
Oh, because of our, Gaussian laws,
It's a line charge too, so.
It's a line charge, right? So think about it like this. There's a long line of charge, let's say an infinitely coaxial cable. Okay. The field lines are always going away from the charges. Right? So if you are going out in this direction, and let's imagine that you wanted to have a field line that went this way. Now there's a charge under here, which is actually pushing it out in the same direction. So you have this symmetry along the line of charges. So they all go out radially. Right? That's the intuitive way to think about Gauss's law.
So how come the outside doesn't mess it up?
So what happens on the outside? On the outside, the total charge again goes to. That's the only reason why you don't have field on the outside. Okay. Because every field line from this one connects to a location on this. Okay. Positive to negative, negative to positive. Okay, so we did it. Or you did it in your notes and I did it last time. So S looks like what?
Well, 1/mu0, then times the line charge density over 2 pi epsilon.
oh, do you want to find an answer or?
I want the final answer, please.
Oh,
Because I wrote this down, I think 3 classes ago.
Yeah.
Lambda I over 4 pi squared.
Lambda I over.
4 pi squared epsilon naught.
Okay.
And then times 1/s squared.
Okay.
I thought, isn't that for power? Like when we solved it for power?
Yeah.
That's the funny vectors.
That's the S. I haven't finished.
Okay.
I've only found S.
Okay.
So now we need to do something, right? What's that?
You said take the integral of it?
That's correct. Now we need to take the integral. So how do we do that? How do we do that? How for y I take integral?
For volume. The integral.
Okay, let's do 3 integrals. Okay, nothing better than 1 integral. Only thing better than 1 integral is 3 integrals. 2, and then 3, and then eventually 4. Okay. Oops. I think that's pink. Alright, and I'm gonna pop this in here, and then I'm gonna collect all the like terms, okay? And I pulled out all the constants. Now, how do I write the integral? I need the integrands. I need
Well, you're going
coordinates,
A to B
right? A to B in what?
in the R hat direction.
I don't have
It's
an
hat, it's
okay, R hat right here. So A to B, good. Is that it, just S hat?
No, there's also E hat. And
Well, just to finish up the thought about S hat. But just write the word DS now, or what am I writing?
Oh, yeah, it would be yeah.
Is that it?
no, there's something else.
Because it's in cylindrical, whenever we go from Cartesian to cylindrical, we always have to remember that d phi doesn't add a length.
Oh, you need an S.
You need an S.
yes.
Good. All right, what else? DZ, does that seem fun? Okay, and which way is DZ?
You just like go,
Okay, yeah, let's imagine that it has a fixed length.
Okay.
So let's go 0 to L. I just introduced a thought, and it'll fall out. Okay? And you said DL, or sorry, DC. Good. And then anything else?
B5,
Okay, what does that mean?
0 to 2pi.
0 to 2 pi. So the full circle, we're gonna integrate over the whole thing. Okay. Let's imagine that I wrote smaller this time. Okay. All right, what do we got? What's the integral of 0 to 2 pi? 2 pi, very good. Okay, so the 2 pi hits the 4 pi here, and I get mu naught lambda I over 2 pi. Okay. What's the integral from 0 to L of dz? Right. I'm gonna add that right up here. Okay, now the hard one. A to B of 1 over S dx.
B or
What's that?
B already.
Bada bing, bada boom. Make sense? The hell did I write?
total amount.
So we have a coaxial cable. Let's remember physically what we're talking about. So you give your friend the aux, right? Because that's what a coaxial cable is. Okay. So you hand him the aux, he plugs it into their phone, and they start playing music. Okay. At rest,
There's no current.
there is current.
Oh,
At rest,
Yep.
the coaxial cable is not physically moving, and yet there's momentum. Because otherwise, PEM would be 0. Okay? If there wasn't momentum in the fields themselves, right? Then this would be 0. When we talked about this paradox, two charges acting on one another, creating forces in different directions. If you just look at those individual forces, they won't be equal and opposite in the p direction. That's because between them, the fields themselves are carrying momentum. They're holding on to it. We'll need this really, really important for light. Okay. How can light, which is energy that is created on the surface of a sun that's 93 million miles away, melt my candy bar? This garbage right here. Right? But of course, anyone who watched the solar eclipse,
I do have glass.
on Saturday, yeah, one thing that you'll notice, it got darkish, but also cold. So we need a little bit of that because we don't want to die. My friend was like, easy solution to global warming. I was like, no, everyone would die. What was that? Yeah, blot out the sun. I think the machines tried that in the Matrix. Didn't go over well. Okay. Did you just watch Matrix? Yeah, I can't get distracted by that. But we have to address this later. Okay.
That was a popcorn. Sure.
Oh, it's fine.
Yeah.
Okay, okay.
All right. Do we want to see one more?
Is it about power?
No, about one. One power instead? Power is just S.dA. If anything, that one's easier. One less integral direction to do. But do you see the power? I mean, sorry. Do you see the utility? Right? They're really beautiful coupled sets of equations. We just find out the fields. We just find out the electromagnetic fields for both of these objects. We can fully determine their momentum. We can fully determine their power. And we can fully determine what forces they have on other things. So all of that garbage we were doing about fields of art law and trying to find B and E forever and ever, and you're like, well, I'll never use this. It turns out you can generally use all of them, as long as you can describe the situation well enough. Okay, you have some unusual configuration in your, CCD structure, where you have maybe mounted platforms next to, flat things, and you need to calculate what the E field looks like. All right, you go through, you calculate it all. Then you figure out what the force is going to be. Boom. Once you figure out what the force is going to be, all right, you back it out right here. You figure out what it's doing to your sample. Okay. I'm trying to talk condensed matter, but I really don't know anything about condensed matter. I mean, other than I know that matter is small. Okay. Okay. Do you want to see one more or we're done? Raise your hand for one more. Outvoted. All right, let's go. Infinite. Yeah, the 3 people who raised their hands win over the people who don't raise their hands. Because if no one raised their hands, then I wouldn't do it. But even if one person asked. Okay. So here's what we're gonna do. We're gonna look at a parallel plate capacitor, an infinite parallel plate capacitor. Okay, and you're gonna become experts in this, right? Okay. So I have, say, sigma up here, minus sigma down here, for example, and E field goes like that, okay? And let's say there's some separation, like D over 2 or something. Okay. I would like to know, let's call this 1. What is the force per unit area on, why does it look so bad? Is this knowable?
Yeah.
Yeah, is it easy? It is really easy.
We just need to.
Not in one line. But it is close enough.
So it's not one line? Or is it one line?
It's not one line,
Okay.
but it is conceptually very straightforward. Very similar to the other problem we didn't do. But we didn't do it. Well, we set it up. We wrote the e's.
It'd be like that for the column, we can get rid of all the beat and just go.
Good. So there's a couple things that we want to do, right? Simplification we want to make. One, we want to figure out the stress tensor. We know that in the stress tensor, we're not gonna have any B components, so we're not that stressed about the B components. Right?
So there's no B field in this?
But you tell me,
Are there B fields?
Is there moving change?
there's not a moving charge, then there's no. Good. Is that always true?
What?
Is that always true?
If there's no moving charge, there's no big field?
Is that always true?
I
Well, there's
think
no
changing
free
big field-
charge.
Okay, so there's a little corollary that we'll get to on Thursday, but Isabel's rule is perfect, right? Because the first thing you have to ask yourself, is anything moving? And if nothing is moving, if it's totally static with time, pretty good chance you don't have a B field. Right, unless I tell you there's a static current. But then really in the bottom of your life, like that's not really static, you liar. Okay. Okay. That make sense? Cool. Okay. So what does this look like? B is 0. E is that's correct.
Yeah.
Okay. So what's our tensor look like? I lied to you earlier, so I didn't actually write it out. Very bad, even though I said it specifically at the beginning of class and then I forgot it when I was talking about it. But we're gonna write it out, we're gonna correct the mistake. Okay, good person owns up to their mistakes. Okay, up here in the XX position. Is there an X component? No, and previously I accidentally stated that that would make this term 0, right? But before that, I had to try to remind us that what is the second term in the tensor?
It's what?
The.
E squared.
It's E squared. And is that just EX squared?
It's all-
No, it's the whole thing. Okay, so we have to remember that this is 1/2 E squared, because I forgot it. What about here?
That's 16 what?
And that is,
Zero.
this is 0. This one,
Zero.
this one,
Zero.
this one, this one. This one.
0,
There we go. Okay, all right. What about this one?
something.
Good, very good. What something is it?
Still the
Oh, see.
1/2 E squared.
Still 1/2 E squared?
Yeah.
Very good. And this one?
Easy.
Easy squared, very good. And I know it looks disgusting, I'm sorry. Okay. And then we're done, right? Yeah. I'll let you do that. It's pretty straightforward. You get the answer you expect. It's literally exactly what you think it would be. So you may have even done this problem. I think it was in chapter 2.
Yeah.
All right. Okay, so there, you have it now. You have the Maxwell stress tensor, you have the pointing vector, and now we get to go directly into waves. Okay? So start reading chapter 9 if you haven't already. We might do it a little bit out of order in the book, so make sure you brush up on your wave terminology, because we're really gonna jump from the idea of fields and how fields now fluctuating in time with all of the tools that we have give you the most important phenomenon of your entire life, which is light. You think it's gravity, but it's not. It's light.
Chapter 9.
What's Aaron's looking back? Aaron's not here. I'm putting a break thing on.